Okay, so today we're just going to look at the final thing in our normal distribution chapter from the stats course, and that is, of course, hypothesis testing using the normal distribution. Now, we are already familiar, or we should be by this stage, with what a hypothesis test should look like in terms of the workings. And so the key thing, which I think we'll just start off with, is some of the similarities which we're going to expect to see. The first thing is, as we already expect, we're going to have our null hypothesis, H0, and we're going to have our alternative hypothesis, H1, exactly the same. Now, we've seen that in the binomial, where I think we use the letter P for probability equals as our null hypothesis. And we've also seen it, haven't we, in our correlation hypothesis testing, where I think we use rho as our hypothesis letter. Well, for our normal distribution, we're going to use mu as our key letter. So our null hypothesis will always be mu equals. Our alternative hypothesis will be obviously a combination of mu is greater than, mu is less than, or mu does not equal than, depending on whether, as we already know, it's a one-tailed or a two-tailed test. We will expect to see a significance level, so there's another similarity. It works exactly the same way, as in this is so unlikely it's going to make us to change our mind. That's sort of what my best interpretation of significance level would be. And like I said before, the structure of our question should look pretty similar. Key difference for our normal hypothesis test is that we are going to need to take something called a sample mean. What we're doing here is we're testing a sample rather than a population, and then we're going to take our judgment from our sample and apply it to our population. So just a very quick example, and it's always the same manner in which we achieve our sample mean. If we have a statistic, x is distributed normally 9 0.15 squared, for example, our sample mean we would refer to as x bar, and that would be distributed 9, so the mean hasn't changed. And the key thing is that our new variance would be the old variance divided by n, where n is the number of items in our sample. Okay, so it's always going to be that sort of manner in which we achieve that, but we need to take a sample mean as part of an early stage in our normal hypothesis test. So let's have a look at a couple of examples. These are the ones from the book, so by all means have a little bit of a look. I'm going to call this first one regular, the easy way of doing it, I would suggest. And it's based on example 14. Now, example 14 says we're talking about the amount of juice in a carton. So let x be the amount of juice in the carton. Remember, you need to specify your statistic. And we're told in the question that is distributed normally 63 squared, where 60 is the volume of our carton. So straight away, we can say our null hypothesis is that mu is equal to 60. The status quo is what they're saying the status quo is. There's 60 millilitres in our carton. The key word, and we should be used to sort of reading the question with this lens, is the company is overstating the mean amount of juice. There's a complaint. So if they're overstating, that means actually there's less juice in the cartons than they're saying they are. So our alternative hypothesis is a one-tailed test, should be mu is less than 60. Now, we're also told in the question that we've got a 5% significance level, and we're also told that we've got a random sample of 16. Okay, so I'd suggest writing all of our key information at the start of our question. Now, if we have already got our distribution for x, we're going to take our sample mean. Here it is straight away. 60 is still our mean, and what we're going to do is we're going to use our old variance, which is 9, and we're going to put that over the number of items in our sample, so 9/16 is our new variance. Obviously, that does mean our standard deviation is 3/4. So, in terms of our actual hypothesis test, this is our regular one. It's the one where we get given a value to do our test on. And it says that the inspector finds that the mean amount of juice per carton is 59.1 millilitres. So whatever symbol we've used in our alternative hypothesis, we're going to use that in our calculation here. We need to find the probability of our sample mean being less than 59.1, which using our statistical calculator comes out as 0.1151. So, in terms of our conclusion, and this is, again, just a reminder that the structure should be very similar to all of the hypothesis tests we've ever done, we need to do a conclusion here. So, as 0.1151 is greater than 0.05, our significance level, we're going to accept H0. There isn't enough evidence to suggest that the company are overstating the juice in the carton. Okay, our current belief about the capacity being 60 is correct. So that is how we're going to do an ordinary hypothesis test using the sample mean when we're given a value to actually do our test off. Same thing with two-tailed test or greater than, whatever it is, it's going to look something like this, please. So let's have a look at a second example, and this is based on example 15, using critical regions. And we know that we can do critical regions for our other two as well. Just a reminder, critical region is going to use an inequality. Critical value is going to be the first value in that critical region, which makes us change our mind. So, example 15, let D be the diameter of bolts being produced, obviously. D is distributed normally, 0.58 millimeters, so it's 0.58 centimeters as our mean, and 0.015 as our standard deviation. Straight away, null hypothesis, mu is equal to 0.58. Now, reading the question here, be careful. Key thing, if you mess this up, you messed up the whole question. 50 bolts are taken from the next production to see if the mean diameter of the bolts has changed. There it is, has changed. Not has increased, not has decreased, has changed. It doesn't specify whether it's got bigger or smaller. So we are going to do a two-tailed test here. Mu is not equal to 0.58 as our alternative hypothesis. You get a mark for that straight away. Now, bear in mind it's a 1% level of significance test this. We are going to be thinking to ourselves that we need to split that significance level at either end of our distribution. And we're also told, and again, please do write this down, that n in our sample is 50. So first things first, if we've got our distribution D, we need to get our sample mean, D bar, distributed normally 0.58, 0.015 squared over 50, okay? Exactly the same process to get our sample mean. Don't worry about working this thing out, okay? Just leave that as it is and let your calculator take that on later on. Don't lose any marks for not saying exactly what that is. And we certainly don't want to round it at this stage. Now, key thing here is that we're going to use our standard distribution, which is something which we covered in the video not long ago. This is our situation for our D-bar distribution. We know it's centered around 0.58, it's symmetrical, our bell curve. And what we're saying here is that we want to understand the two regions at either end where our probability is going to be 0.5%, 0.005 as a decimal. What we don't know is what these two values are. So what we're going to do is we're going to convert from our D-bar picture to our Z distribution picture, which we know is symmetrical around 0. Again, though, the tails will still be 0.05. Now, you've seen this formula before. I've just incorporated something else here. It used to be Z equals X minus mu over sigma. For the purpose of this question, I'm putting it as Z equals D bar minus mu over sigma. Now, rearranging that nice and quickly to get D bar as a subject, because that's what I want to find out ultimately, I get Z sigma plus mu. Now, using the inverse normal distribution on my calculator, what I want to do is I want to go inverse normal and I want to put the right-hand tail to be 0.005. Using the Z distribution, comes out as 2.5758. That is this value here. Because of symmetry and because it's symmetrical around 0, straight away, therefore, this value must be minus 2.5758. So, with these values up here as well for mu and sigma, what I'm going to do now is I'm going to put these values for our Z back into the D bar equals Z sigma plus mu, and I'm going to come out with these two values for D bar, 0.5854 and 0.5745, which, you know, are what I was expecting, one above, one below, not too spaced apart. So, to finish off this question, the critical regions will be if D bar is less than 0.575, that's out this way, or is greater than 0.585, that's out that way. So there's our critical regions. Now, part B of the question says the mean diameter of a sample of 50 bolts is calculated to be 0.587. Well, as soon as we see this, and this is why critical regions are quite nice, we can say straight away we're going to reject H0 and we're going to accept H1 because 0.587 is greater than 0.585, so it lies in one of our critical regions and is therefore significant and is going to make us change our mind. So, hypothesis testing, key message, keep the structure the same, but sample mean as a key little difference to all of the hypothesis tests we've done previously. Thanks for watching.